just.
I'll be traveling tomorrow, but I can.
Okay, so today we are very happy to have Bruno from MIT, and he's gonna tell us about the quarkonia in the quark-gluon plasma, some recent theoretical developments.
Okay, well, thank you. Thank you so much for having me here. Thank you for being here so late in the year and so close to the holiday season. I hope I'll give you an interesting talk, and hopefully, I'll get to explain every single one of the words that are up here in case that these are new to you. So what I'm gonna talk about today is about quarkonium in the quark-gluon plasma, specifically about quarkonium transport, thinking about the phenomenology of heavy ion collisions, but in some sense with focusing on the more theoretical aspects that you have to understand in order to properly set up this problem and understand what you need to calculate if you want to make predictions of interest for quarkonium physics and in heavy ion collisions. So first I have to be able to change slides. Okay, so first I'll give you a broad picture of why we are interested in quarkonium and heavy ion collisions, and then I'll start going down what we actually need to calculate and why. So I'll start with a claim here, which I'll substantiate in the next few slides, which is that heavy quarks and quarkonia are very interesting probes of the quark-gluon plasma. That is because since heavy quarks are, well, heavier than, have a mass scale much higher than lambda QCD, they don't thermalize together with the rest of the soft QCD degrees of freedom that lead to a quark-gluon plasma in a heavy ion collision. So they serve as external probes of the system. And well, to actually use them as probes, we need to understand how these objects behave inside a thermal QCD medium to first approximation. We need to understand how to propagate a single open heavy flavors and a pair of flavors that can bind and unbind into bound states of heavy quarks. So what I'm mostly going to focus is the second bullet here, how these heavy quarks can bind and unbind together, and how we can use them as probes, as a thermometer, if you want, of the quark-gluon plasma. So first, let me unpack some things I said, but maybe a bit too quickly. What is a heavy ion collision? A heavy ion collision is a process by which you smash together two new atomic nuclei. In this case, it's a lead-lead collision that recreates what you'd have at the LHC of two highly Lorentz contracted nuclei, which just go into each other. And after they smash into each other, they create a plasma for a short time, and then this plasma starts expanding, freezing out, and giving you a bunch of hadrons and all of the QCD zoo of particles that you can get. And what interests me in this picture here is the evolution of the plasma in between the time of the collision and somewhere around here, 10 Fermi, after the collision, where you still have a thermal medium, say around, oops, well, I didn't manage to stop the video in time, but well, you see where I'm going with it. I'm interested in this QGP phase that's formed shortly after the collision and how to understand its properties. So this is the more artistic depiction of the process I was just showing you, where you start with two highly Lorentz contracted nuclei, you collide them. There's some thermalization process that goes on very quickly in 1 Fermi over C. And then there's a reasonably long time evolution of this quark-gluon plasma for 9 or 10 Fermi after it freezes out and particles just free stream into the detector. So this, if you're curious about why this choice of artistic depiction, and if it looks like cosmology, that's not an accident. People try to make the analogy of between a heavy ion collision and a little Big Bang, if you want, where you produce matter initially in thermal equilibrium, which then expands and freezes out and gives rise to all sorts of structure that you can measure at the end of the day with an appropriate detector. Well, here I'm going to be interested in probing this phase of high temperature QCD matter using quarkonia. And what is quarkonia? Quarkonia is a bound state of heavy quarks. In this case, I have either a pair of charm and anti-charm quarks, a pair of bottom and anti-bottom quarks. And you can look them up in the particle data group website if you want, and you'll see that their tabulated masses for the different bound states that they can form. Say if you can form an analogy to the hydrogen atom, you can form 1s, 2s, 3s states, etc. With binding energies, so energy splittings of a characteristic size of a couple hundred MeV, which conceptually makes them an interesting system because you have let's now forget about the fact that there are B or C quarks. Let's just have a heavy quark pair. There are 3 scales in this problem. One is the mass of each individual heavy quark. The next is the size of this bound state, how big in space the system is. And the third is the level spacings between the different bound states that the system can form. And I've drawn here the length scales associated to those mass scales next to their binding energies, the typical size, inverse size, and the mass. And you see that there's a clear hierarchy, at least for B quarks. So this makes it interesting to ask, well, what if I have yet another scale, which is the temperature of the quark-gluon plasma that you'd form in a heavy ion collision, which is again, it falls into a well-defined hierarchy here of these scales, and you can draw it here to give you a sense of what it is. It's also useful to, well, since some of these scales are high energy or small in position space, it makes sense to, well, to zoom out and compare with the actual size of the fireball you form in a heavy ion collision, which is about, well, the radius of gold or lead is about 5 Fermi. So if you compare that with, which is basically the transverse size of the quark-gluon plasma blob that you'd form in a collision, you'll see that the size of this bound state will be comparatively small. So what you can do to try to understand how this system evolves in this thermal medium and then be able to ask questions about what you expect at a detector when you ask questions pertinent to the dynamics of B and C quarks in the medium. You can use this hierarchy of scales to set up an effective theory description that gives you control and power to do calculations. And the main ingredient here is to treat this bound state essentially as a point-like particle, which is well, because of what I just showed you, very small compared to the typical length scales of the medium, and it will interact with the quark-gluon plasma through dipole type exchanges, so that you treat the QQ bar pair as a small color dipole, and there will be long wavelength excitations from the medium that will be able to make this state transition between a bound and an unbound state. This transition will also change the color state of the medium because the gluons are color charged. So sorry, the color state of the QQ bar pair because the gluons are color charged. So you have this nice picture where you can transition onto each other, which by the way is analogous to what you'd have in hydrogen, where you want to ask about the transitions between different energy levels by exciting an electron from one orbital to the next. So here, well, you can write out an interaction Hamiltonian for this type of exchange, which is essentially an electric field insertion, just because you're expanding in a dipole, in a multiple expansion. And then you have a creation and annihilation operators that essentially say whether you create or annihilate a singlet or an octet state.
Go back to something. I just want to understand something. In your original picture of the analog of the Big Bang, that period of about 5 femtometers, you want to treat it as the quark-gluon plasma as an equilibrium system, roughly.
Yes, as a system in local thermal equilibrium.
What's the evidence that that's a good approximation? Is that mainly lattice or numerical or something, or?
No, well, there's plenty of, one thing you can look at is flow of light particles. And the spectrum, the momentum spectrum, if you want, you look at your detector and you ask how many particles do I have with this momentum, and you can fit those to a thermal distribution, basically.
So there's a good notion of temperature.
Yes.
Spatially homogeneous across the plasma?
Well, it's not homogeneous. What you do is you do hydrodynamics essentially. You assume that you have local thermal equilibrium, and after a short time, you only have to deal with the evolution of some of the conserved charges, well, it won't be homogeneous because it's a fireball.
Yeah.
But the assumption here that I'm working with is that you have local thermal equilibrium, and that since this system is small compared to the scale of the whole system, locally we'll see a temperature that I can feed into this calculation. But,
yeah, there is spectrum, and this involves a whole bunch of particles, including resonances. They all fall into basically a thermal model with the same temperature and chemical potential. And there is also you can trigger on the collisions which create fireball, which is not azimuthally symmetric, because most of the collisions are not central. So this creates a kind of almond shape in the cross-section region, and it expands not isotropically, right? Gradients in different directions are different. So you can apply hydrodynamics, and it agrees with experiment. So not only it looks thermal, but it also looks hydrodynamic as well. So it's pretty.
So you say that 5 femtometer timescale roughly, it looks like hydrodynamics is a very good description of that.
Yeah, it looks like hydrodynamics starts applying even before one Fermi.
yes,
Before one, okay.
that was
One of the mysteries of the universe.
Well, yes, I mean, hence what you ask, right? Some people will say that they understand why that happens, but yes.
So Bruno, you want to treat quark anti-quark as a point light object, and ignoring 1s, this structure like 1s, 2s, or that.
I'm gonna show you an effective theory that decouples those two things. So on one hand, we're gonna look at the internal structure of the QQ bar pair as well as energy levels and wave functions that you can treat non-relativistically. And that will be coupled through this dipole type exchange to the quark-gluon plasma. So I'm not gonna lose all sensitivity to what the internal structure is, but I'm gonna expand using the fact that this is a small number. And the first interaction I get is something of this type. First let me get here. So what I'm gonna actually be thinking about is modeling this with potential non-relativistic QCD, which is an effective theory that you get after essentially integrating out all of the modes of QCD that you need to form the bound state, if you want. So the comparatively short wavelength compared to the thermal scale of the medium, and then use this system as non-relativistic as a system where you have where this process of integrating out modes gives you some kind of interaction potential between the heavy quarks, neglecting the fact that you have say that you have a higher Fock components where you have more gluons and addressing this state, assuming that you have a potential model where you can talk about two heavy quarks bound together with a given interaction strength, where you have resummed some of the gluons that mediate this, and you can do this in electromagnetism as well for hydrogen if you want. And then you take this system, you assume that, you've done the hard work of integrating those modes out and telling you what the bound state actually is, what the bound states and actually are. And then you want to, and then because the energy splittings are of magnitude comparable to the temperature of the quark-gluon plasma you form in a heavy ion collision, you can ask about, well, what are the effects of this system interacting with the environment through one gluon exchange types or multi-gluon exchanges if you want. And then, well, you can identify 3 timescales in the medium. One is, well, the intrinsic timescale of the subsystem of the heavy quarks, which is governed by in what states can they bind in. So 1s, 2s, 3s states if you want, which I'm gonna assume here they're encoded in single particle Hamiltonians. Then there's an interaction term where you can make these states transition into each other by inserting a gluon from the medium, from the quark-gluon plasma. And then finally, you have the whole QCD Lagrangian for the light degrees of freedom that has, for these purposes, one typical scale, the temperature, but you should also throw lambda QCD in there.
Sorry. Why non-relativistic?
Why non-relativistic? Because I'm looking at, I'm going to be focusing on quarks of well, bottom quarks mostly, which are, their masses are 4.5 GeV. And the medium that I have that's formed a heavy ion collision is about 200, 300, 400 MeV at most. So if I go to the rest frame of the heavy quark, you can't really move it around with random kicks from the medium due to these momentum transfers of order a couple of hundred MeV. So you go to the rest frame of the heavy quark, assume that it stays there, and it does stay there because if it decays, it will decay electroweakly, which will take much longer than the lifetime of the fireball anyways. So you look at the system from that frame, and there, because there's nothing that is going to kick the heavy quark around, there's no other hard particle that's going to make it move, that's going to give it a large momentum fraction relative to its mass, you can treat it non-relativistic. That's good for bottom quarks. For charm quarks, it's less good because there you're closer to the temperature, and there's actually evidence. Well, there's from simulations that you might achieve actually partial thermalization of charm quarks with a medium. For bottom quarks, you have a more than an order of magnitude of separation that prevents them from moving around too much.
HS and HO are these numbers?
These are single particle Hamiltonians. So
Which is grad square over 2m?
yes,
Just
grad squared over 2m plus a potential if appropriate, and plus a potential for the singlet in this.
What does it mean, potential?
Oh, means that you have some that you have by integrating out the higher energy gluons, you've essentially you try to construct a, well, not you don't try, you construct a, say, a Cornell type potential where
between 2 quarks.
between the 2 quarks. And these S and O are creation annihilation operators for the pair, not for one individual, not for each individual heavy quark. They tell you about how a singlet propagates through space-time and how an octet propagates through space-time. So the 2 different configurations of color that you can have for a heavy quark pair.
If this is are these point-like treated as point-like fields or?
S and O, yes, they're treated as point-like.
But then I don't, where the potential can come in. It's
well, yes, I omitted one line here. So you separate this into 2 coordinates. You have one coordinate where you have a relative dynamics where this potential plays a role, and you have a center of mass dynamics, which is the one that the E field here is coupled to. And those things are separated by construction here. But yes, I omitted one integral here in that sense, which is the center of mass. Yes.
And you said S is the singlet and what is O?
The octet. So
what is R, the integration over which is being done?
this one, this is
Coordinate?
This is the relative coordinate of the QQ bar pair. And but all of these which couples to the wave function of each state, which is not very explicitly represented here. But this R is the R of the wave function of the relative position between the heavy quarks, and all of these fields. So E here is only evaluated at the center of mass coordinate between the two. So essentially, this comes out of taking a mu and expanding around R and a capital R, which I'm not representing here, in a series of on lowercase r.
So this is a Lagrangian, and the degrees of freedom of this Lagrangian are
Well, you have the light.
wave functions. So it's a second quantized.
This is yeah, it's a quantum field theory coupled to a quantum mechanical system, to a second quantized quantum mechanical system.
Second quantized quantum mechanics.
Sorry, very basic question. Why are integrating dr there? This is Lagrangian density. Is there like some non-local terms or something?
Why am I integrating this?
Yeah, it's like the non-relativistic case, we have like the local term, and then you have the Coulomb potential that has a non-local interaction. Is this like what? Like why is the kinetic term there, for example? I would expect the kinetic term to be local.
Well, I am keeping, I mean, at this level, I am keeping some sense of non-local interactions in the sense that I have a potential explicitly there. And in that sense, I am coupling what S dagger does at one point to S at another point. And that's because of non-relativistic construction here. I am assuming, yeah, I need to accommodate a potential for this. Yes, and there are more intuitive ways of writing.
So you are saying, maybe trying to answer the question, that if I do the variation of this Lagrangian with respect to degrees of freedom, such as S dagger, I will get a Schrodinger equation for S.
Yes.
Is that how you?
Yes. Yes, that is you'll get a Schrodinger equation.
That's why there is time derivative.
Yes. Get a Schrodinger equation for S, plus some terms that you get because of interactions with the medium.
So there's some mixing.
Yes. Okay. So what do we want to use that for? We want to construct these kind of processes where we have in a more QFT type diagrammatic language, where we want to start with a singlet state and transition to an octet state through some interaction with a medium, and we want to know what's the rate of this process. And as it turns out, as I'll describe in the next few slides, there are two correlation functions or distribution functions that you have to calculate to determine these rates, which we have denoted by G++ and G-, which the reason why should become apparent in the next slide. And so the idea is to resum all of these diagrams plus all of the higher order contributions in the coupling constant expansion to make something like this, where you have an initial singlet state, and because of interactions with the quark-gluon plasma, you transition into an octet state and vice versa. So the answer to that question is these stapled shape looking chromoelectric field correlation functions. And let me tell you why this is the answer to that question, instead of just going through the formula. So what this does on the left here is to say that at early times, before some time at which some interaction happened, there's no operator insertion. That's because you have a singlet state which is not color charged, so nothing is happening without it interacting with the medium perturbatively, in the sense that since this interaction comes from an expansion in multiples, so it's proportional to R times the temperature. This will be small, and you can expand perturbatively and write out a series for this. Then you can insert as few of them as you need to actually get a non-trivial contribution for your physical process. So at some point there is a transition induced by the medium, which makes a state transition into an octet state, which then evolves further in time. But now it's color charged, so you can have one gluon insertions along the way, which you have to resum because the FT expansion is not an expansion on the coupling constant, it's an expansion on the size of the system. So these have to be put back into your observable, and they lead to Wilson lines that you get explicitly here and here. And then, well, you wonder why we have two, only to describe one. That's because if you want the rate, in some sense, you want to take the absolute value squared of this that you can see as a scattering amplitude. So what you end up having to calculate is this correlation function. Same thing for the inverse process.
There is this Wilson line, W1, W2 are the two Wilson line,
Yes.
and there is some Wilson line that on top of
If you take if you take them to be spatially separated, you can argue that you can argue that essentially by summing
Is it that?
Hmm?
I'm sorry.
but you can argue also by resumming the interactions of so-called Coulomb interactions, which is what you have. By doing that, you can reconstruct a Wilson line at infinite time. But well, I mean, it's obviously something like this needs to happen because you need a gauge-invariant object. How you construct this, you have to work a bit, and I fear I don't have the technical details here. But you can get this by arguing that you need to do a more complicated resummation than what I showed you here.
So this Wilson line is a fundamental representation or adjoint
Adjoint
representation?
representation
Adjoint because it's
Because,
sourced by
an adjoint point
source.
charge. Yes.
Basically, it's sourced by the transition or dipole.
Yes. So you transition from a singlet to an octet,
To color octet.
and the octet is in the adjoint. You get an adjoint.
It should be simple, but I maybe you can help me. So suppose I consider electrodynamics. Let's say positronium,
Okay.
right? It has two states. And I want to describe the decay of the, orthopositronium into parapositronium or whatever.
it's colorless.
But that's color.
So it is colorless. So where does the color matter here?
Oh, because the gluon that you take from the medium here is color charged. So you make it. So the gluon comes from the adjoint. So if you start with so if I want to use a gluon to make my state change, and absorb that gluon or emit that gluon, I still have to obey selection rules.
To have different charge.
Different
Octet.
Yeah,
With singlet absorb, then propagate as an octet.
that's why you need the Wilson line
Yes.
here, but you don't need in quantum alternative.
Right.
Yeah, because there's no adjoint.
Right.
Right.
Yes.
Quantum is neutral.
Exactly. Yes, and you can do the same thing for the inverse process. Instead, here the idea is that you start with an unbound state in the sense of color, for which you need Wilson lines. At some point, you get a kick from the medium, which makes you transition to a singlet, and after that, nothing happens. And those again give rise to this type of correlation function that you have to calculate. In practice, if you're really in in the infinite heavy quark mass limit, then the center of mass position won't really move much, well, won't really move, strictly speaking. So you can just think about the case where you have the two positions I showed in the previous slide at the same point, in which the correlators simplify to a bit, not completely, because since you're still doing, in a sense, linear response in a thermal background, one of them, the dissociation one, simplifies to just an electric field correlator with an adjoint Wilson line between them. But the one for recombination still keeps the memory of the fact that you initialized the system in a state where you had a point color octet charge sitting there. So the color degrees of freedom had enough time, because we're pretending that it sat there for infinite time. So they had enough time to thermalize, and you need to include them in the initial density matrix, which gets you a more complicated object, because now you cannot cancel these because of operator ordering problems, or well, they're not problems. They encode the physical state, but if you naively you'd want to cancel them, but you can't.
Can I ask another question?
Yeah.
Obviously Wilson lines are important here.
Yes,
So I just want to make sure I understand why they are straight.
straight and
Why they
as
are
opposed to
fixed,
wiggling.
as opposed to being
Bec-
whatever else.
Oh, because
what-
of because of the assumption that you're working in the infinite heavy quark mass limit. So you assume, so if the wiggles here will be proportional to, will be controlled by the
Okay,
the kinetic.
so let me then ask this question differently. Why should this Wilson line be aligned with the position of the heavy quark in the past or in the future? Why couldn't it follow some different trajectory? As long as it connects.
Oh, because that is what say that you write the current associated to the color current associated to having a point charge at some point in space, and you write that in your Hamiltonian, and say that you write the QCD Hamiltonian H plus this point charge there, which, well, you write as a J, which is a delta function coupled to A. That gives you exactly a Wilson line at that position. So if I say that you have so the statement that I have a point color charge sitting at some position and it's infinitely heavy and it's not going to move, is the same as saying that if I want to fulfill Gauss' law as seen from the environment, because I have a point color charge there, the Wilson line is how this happens, is how this is encoded. So the reason why this Wilson line stays there is because this follows the trajectory of the heavy particle.
Can I say that that if you insert into the partition function the term, or in the action, the term corresponding to a heavy quark, that will insert into the partition function, or the integral, which describes it, basically Wilson line operator.
Yes. Yes. So that is what I'm saying. Which is also, and in that same way, you can get why this happens down here. Why you have to include it. What you have to do is take some imaginary.
Right. So if I were inserting a heavy quark, that would be a fundamental representation Wilson line. What do you insert to get the octet, to get the adjoint Wilson line?
From
Why do you get adjoint Wilson line?
I get an adjoint because I'm by construction I'm saying that the state of the system, well, the point defect, if you want, that I'm inserting in the theory can be either a singlet or an adjoint. I'm not allowing here for the possibility of having a fundamental charge sitting there by itself. That's why I don't get one, but I'll actually compare with that in a few moments.
I have another Wilson-line question. So, why isn't the right thing to compute not basically the expected? So you have your medium, and all of a sudden, your singlet becomes an octet, and there's presumably there's another colored excitation in the kind of bulk of your medium. So if I think of the intermediate state, I would have kind of two particles with a space-like Wilson line between them.
I mean, if you look at it as time slices of
Of a state.
well, I mean you'll see that in the when you calculate, say, the path integral, and that's time slice. The fact that the rest of the medium will have a net color charge will be given precisely by the integrating, say, over A0 here, which will give you the Gauss law constraint, and this will look like a point source to that Gauss law constraint. So it will tell you that the rest has to be charged with the same charge. But actually following that, I mean, if you can still talk about this object in a fully relativistic way and think about, well, that slicing is arbitrary. I could very well have taken a slice that goes this way, and then, well, it's not obvious to me how you'd interpret that. At that point, I prefer to think of this about as a color singlet object as a whole, and you have some transition probability, say that you're contributing here from a singlet to singlet transition, and then you can take a cut and have the rate of decay to an octet. Well, not decay, but transition. But yes, did I give you a satisfactory answer, or?
Yeah, I think so.
Because these kinds of issues are never been too satisfactory to me anyway, so I'd like to understand them better. But I mean, I can set them up, but I would like to have a calculation that you can do in many different ways and see how the answer to your question emerges. So, but yeah, I mean, I have a couple of calculations, but
yeah. I guess what I'm so in my way of setting it up, the intermediate states would have been kind of gauge invariant in the same Hilbert spaces. But I guess, yeah, you don't want to do this because you want to focus on the heavy quark Hilbert space.
the full state of the system will still be a singlet, a gauge invariant object.
Yeah.
But, so if I'm claiming that I have a deconfined heavy quark pair there, which is in the octet in the sense that they're not coupled to each other directly into a singlet, then the rest of the state of a system must learn of that. And because I changed the color state, because previously I had a singlet in both cases, and I made some exchange where I moved color charge around, so now I have a point. After integrating out the rest, I would see these heavy quark pairs as unbound in a color octet. Then the rest of that charge has to be in the rest of the environment. So it is there. It's just Okay. Okay, a bit of phenomenology now. These are the fundamental objects that we'll calculate in what remains. But how have people used them? What can you get from here? And this is actually quite recent in the sense that these kind of transport formalisms have only taken flight in the last 5 years or so. So one thing that people do with these correlators here in this case is to write out a Lindblad type equation which you can derive, strictly speaking, in a regime where the temperature is quite high compared to the binding energies, which in phenomenology you should not take too seriously, because this hierarchy is really never satisfied strictly. You can still write it out, people still do it and fit data and don't do too bad. And the idea here is that essentially since the plasma has high temperature, all of the energy transfers between different states will look like low energy physics. So what you can essentially encode all the dynamics into transport coefficients, low frequency limits of the correlators. And what they defined is that the zero frequency part of the time ordered correlator in this case, they call kappa and gamma, enter their Lindblad equation in that way.
How does gamma enter?
Oh, gamma enters through delta H, which I have not written here because it's a huge matrix. But, yes, it contributes to the self energy, if you want. Well, there's also other limits you can take, but then you give up on the coherences of the density matrix. That you can write out a Boltzmann type equation with dissociation and formation rates, which are also given in terms of these correlation functions. And they're evaluated at the energy transfer that you need to have to move from one state to the other. And in this case, these correlation functions represent the effective distribution of gluons that can mediate this transition.
So this is the rate when you say dissipation. So the first
Dissociation.
rate is the rate of what process?
The first rate is the rate of having an octet there and asking what's the rate, having a singlet there and asking for what's the rate at which this transitions into an octet state.
Why is it called dissipate?
No, dissociation.
Dissociation. Why is it called dissociation? Because
You're dissociated, yeah, exactly. And this one is the formation or recombination, which is proportional to the distribution function of pairs in the octet state, basically. So in the dissociation rate, you just need to know that you have a singlet there somewhere. In the other case, when you have a formation rate, you need to know, in this description at least, I have a QQ bar pair here. Where do I have it? And you have to.
This is just reverse process. So.
Yes. Yeah, basically.
And I may have missed at the beginning. You assume that this pair can be only into the octet dominance, right? So either singlet or octet.
Yes.
There's no other.
That is the assumption. Yes.
What else can it be? Just quarks, anti-quark.
Well,
I guess, yeah.
yes, if you only have a quark and an anti-quark, yes, but hadrons are complicated. Well, in the sense that
Heavy and hadrons.
if you have you can worry about
Light quark.
the other components of if you write out a Fock state for this system, you can worry about light quarks and gluons addressing that, and those can also interact.
Open charm. Or something.
But yes, if you say that you have a QQ bar pair and you only want to follow those degrees of freedom, then you can only have a singlet or an octet. Yes. But how good this approximation is to actually describe the physics will also be controlled by how little the very light QCD degrees of freedom affect these singlet and octet states. Because essentially the assumption is that you can define the states without worrying about the very light degrees of freedom that we're only treating here at the level of the thermal bath. Okay.
Sorry, are these related by detail balance? That is, can one get the relationship between G++ and G by balancing this in a thermal ensemble?
Indeed. These two are related. You can prove that they're strictly the inverse process of each other, and then they attain detailed balance, which motivates the fact that you can introduce a spectral function to encode the information into one single object from these two things, and then you can ask, well, what properties does this spectral function satisfy? And it's a bit more complicated than usual because now the dissociation process, the correlator associated to a dissociation process and recombination process are not equivalent because in one case, the initial state has a point color charge there, and in the other case, it doesn't. So what ends up happening is that the spectral function is not odd under frequency because essentially you have two different correlation functions there. You have less symmetry in the problem. And then the spectral function, well, if you write it out explicitly as spectral decomposition, you can see explicitly that it need not be odd. It will for usual correlation functions, it will be odd because these energies here would be the same as these energies here, which are the eigenvalues corresponding to the Hamiltonians with a point charge or without a point charge and point color charge. And that means that, well, you have to work harder. That doesn't mean anything more than that. But this was very confusing the first time we did such a calculation. So this is something we did a couple of years ago, where we just said, okay, this is still an object I can formulate in quantum field theory in terms of Feynman diagrams if I have weak coupling. So let's write it out. And you find, once you look carefully, that there's a term here that is not does not have definite parity, that makes this full object not have definite parity in frequency, which is the sign of omega term here. Otherwise, this would be completely odd under frequency. And this was even more puzzling because now if you compare with open heavy quarks, so having a single fundamental point charge sitting in the medium, then the answer was excruciatingly similar, except for the fact that there was no frequency even contribution here, which made us run around in circles for quite a while. And by the way, I only listed the zero temperature terms here, but they both have finite temperature terms and they agree as well, as does the whole thing, the whole rest of the expression.
Is that NC and NF containing bracket just beta function?
This is
or is it different linear?
no, this is just the beta function in the fall. Yes, the prefactor of this is basically the beta function. You can show that at this order, well, I mean, because we have not shown it at higher orders, but this expression here, as I've written it, up to order g to the fourth is RG invariant. So if you take a derivative here with respect to mu, and you ask how does this coupling constant have to evolve so that this whole thing is invariant, you get exactly the beta function for
G here is evaluated at scale mu.
yes.
So you can absorb this term if you evaluate G at scale omega.
Yes. Yes. Here, yeah, exactly. Okay, so then I want to go and do the comparison with
So isn't that the row fundamental isn't the same object as row adjoint?
No, I'm going to introduce this one now.
This one doesn't have plus plus.
Oh, I have not introduced this object now here. So far, I've only told you that there is a spectral function you can define for open heavy quark diffusion, which I'm going to introduce in this slide that follows. That spectral function comes from this correlation function where you have which represents the physical situation where you have a point fundamental charge, point-like fundamental charge, a heavy quark there sitting at all times. It's color charged, so it can interact with the medium through this soft gluon exchanges at all times. Then the diffusive part of this comes into the fact that you at some point assume that it received a stronger kick from the medium where some momentum transfer is actually affected. And then it just keeps on flying into the future. And what you get here is that, you take the amplitude and the conjugate amplitude and then this trace, and then this is the correlation function you get. And if you want to define a spectral function associated to this correlation function, you get this result up to next to leading order.
So it never disappears. So
right.
and theta is the same.
Say that again?
In the spectral representation, you don't have to deal with two different Hamiltonians.
Exactly. And well, you can again wonder, okay, what makes them differ in this perturbative calculation? And it's precisely that aspect, the fact that in one side you have to deal with the fact that you have transitioned from a state where you have no point color charge sitting there to a state where you do have a point color charge sitting there. And you can, if you just take this difference, you can evaluate it and reproduces the difference I showed you earlier. It is, among other things, because you have different operator orderings encoding different physical processes. It tells you that, well, the state matters, what color you have. And well, you can show explicitly that this whole thing is gauge invariant as it should be, and well.
What is the value of CF?
CF is NC squared minus 1 divided by 2NC.
TF?
TF is 1/2. It's the normalization of the function.
So does the fact that gluons interact with each other matter for this term?
The gluons interact?
That there is a 3 gluon vertex? Because does it matter? So suppose I had it actually appears in the 3 gluon vortex
Yes.
to get that result.
Yes.
Omega cube term.
Yes. This is the only way it appears at a disorder in the coupling. And then, well, you can wonder how this appear if you've shown that this is there perturbatively, what happens non-perturbatively? Can you show that this will be there regardless? And well, quick review of the Schwinger-Keldysh contour. And if you already know everything you need to know about the Schwinger-Keldysh contour, I can just say that the difference between the two correlation functions is this. In one case, you have adjoint Wilson line connecting the two E fields directly along one branch, whereas in the other case, if you if you write the correlation function I showed you as a path integral, you'll see that you have to the Wilson line has to wind around the Schwinger-Keldysh contour, which will give you a qualitatively different setup. Just in case that you don't use this frequently, the Schwinger-Keldysh contour is good to evaluate many things. One of it is expectation values in thermal equilibrium, where you just represent the thermal density matrix as a path integral that evolves along the imaginary time, and you insert an operator at some point in time, which gives you a 1-point function. You can do 2-point functions, inserting an operator some imaginary time tau down the path. And you can also do real-time calculations if you insert real-time evolution operators, each of which you have to represent by its own segment of the path integral, and then you have to close it up because you have a trace here. So this is how you get these two setups. And in one case, here on the right, you have a point color charge at all times. So the fact that the Wilson line is there is telling you that this heavy quark affects the whole thing. Whereas in the other case, the adjoint point charge is not a construction, it's not part of the initial state, not necessarily. And so if you transition to it dynamically, then you have a topologically different configuration for the Wilson lines, if you want, in the sense that it doesn't wind around the Schwinger-Keldysh contour. This leads to differences when you try to extract these correlation functions from Euclidean calculations that you would be able to do in a lattice gauge theory setup. So if you do the heavy quark diffusion case, what you'll have is that you can write things out in terms of this correlation function, which has well-studied properties, and you can write out inversion formulas to determine the spectral function in terms of the imaginary time data you can calculate from the lattice. And you can in principle extract transfer coefficients by taking the low frequency limit of the spectral function. Whereas in this other case, the correlation function that you have to write out has a bit less symmetry because now you have some time with which you evolve the system with Hamiltonian. It has a point charge there, and the other case you don't, compared to the case of heavy quark diffusion where you always have a point charge. So the inversion formula looks slightly different because rho no longer has definite parity. And then, well, if you don't assume anything else about analyticity, the only thing you can write for the low frequency limit is in terms of either the odd or the even part of the spectral function. And well, so once you do that, you say, well, this looks hard because I have to ask friends from lattice gauge theory to do the calculation for me. And I want to have some control over, but as a theorist, I would like to have some control over what these objects do at larger couplings. So we turn to n equals 4 Super-Yang-Mills, where we have holography to do calculations. I'm going to first show you the answer, and then assuming I have time, I'm going to show you how we get to this answer. And the answer is that the spectral function rho fund, which is the one for heavy quark diffusion, that only differed by this absolute value of omega cubed term in the perturbative calculation, and the rho adjoint plus here that I've shown in the orange line are actually dramatically different at strong coupling in the large NC limit. So yes, now I'm going to show you how this goes through. So, and to show you how this goes through, I have to first set up calculation of each object in holography. What you can do in holography is evaluate Wilson loops, expectation values of Wilson loops at thermal equilibrium even by solving for extremal surfaces as determined by a string theory action. And we'll go to action in this case. And you specify the Wilson loop by a contour on the boundary of the CFT, on the boundary of the CFT that is dual to the higher dimensional gravitational theory. And then one has to extremize this Nambu go to action subject to the boundary conditions set by this boundary path. And if you wonder, well, how does that help you to calculate correlation functions of electric fields? Well, electric fields or field strengths in general can be inserted along the Wilson loop by just taking small deformations along the path. So if you have the ability to write out the expectation value of a Wilson loop and small deformations on top of it, then you can evaluate correlation functions of gauge field of field strength operators dressed by Wilson lines, which is what people in lattice QCD do actually to calculate the heavy quark diffusion coefficient. They calculate the difference between expectation values of Wilson loops going through different paths, and that gives that is essentially equivalent to this second derivative. But okay, so I have to also go through the fact that in n equals 4 Super-Yang-Mills, then the natural thing to define in holography is a Wilson loop which has scalar fields as well because of supersymmetry, which is not the standard Wilson loop, and which essentially adds another ingredient into the definition of this object which is coupled to the S5 part of the gravitational description of the theory, which is always there, but in practice we don't usually refer to it because most of the things that you need to calculate in n equals 4 Super-Yang-Mills or for thermal physics that are relevant for heavy ion phenomenology and that sort of thing, ADS5 and holography in the natural sense there is all that you need. But in this case, we found that the S5 does play a limited but important role, because now we have because this is the Wilson loop for a fundamental charge, and now we have to decide what to do when we have an adjoint charge where microscopically we have two heavy quarks there. And so what we ended up doing is, well, physically, the Wilson line in QCD satisfies this property, the fact that if you write an adjoint Wilson line in terms of fundamental lines, the two fundamental lines that comprise it will be conjugate to each other. So if you write this out as a time-ordered Wilson loop, which is closed at its endpoints, the Wilson loop that you will get is a trivial Wilson loop where you have trace of U dagger. And then if you insert electric fields along this Wilson loop, you can get the correlation function we're interested in for quarkonium physics. But the fact that we have this property in QCD means that you would like to have it in your holographic formulation as well. And if you look back onto what the expression of this Wilson loop is, and you want to make sure that the leading answer without deformations is unity, you'll be forced to conclude that the segment that goes up and the segment that goes down along time will have an antipodal position on this extra S5 coordinate. There's another way of arguing for this more formally, the fact that there's also a prescription for more recent though for evaluating expectation values of Wilson loops with only pure gauge fields without the scalars, which amounts to imposing Neumann boundary conditions for this extra parameter n hat on the holographic side, which if you write it out in terms of the field theory is just integrating over n hat and leaving it free basically. But then if you just look at this, you'll see that in real time, this object here is bounded by 1 because it's just a unitary operators. And you can then ask, well, when is this bound saturated? And then you can go back to the expression you had here, just write it out and show that this thing is explicitly 1 if the Wilson lines satisfy this property. And so because all the rest are just highly oscillatory phases when you take the limit lambda goes to infinity. So when you take when you only take the dominant contribution, when you suppress more and more the fluctuations, this is what will dominate. And then you have everything you need to set things up and take a background contour, introduce small deformations, solve for what these deformations do to the world sheet in the bulk, then evaluate the action again and take the derivatives. In terms of qualitative terms, this is not an actual solution. This is simply to give you a flavor of what's most different in this case than in the heavy quark case is the fact that because now you have Wilson lines only say along the real-time segment, the surface will do things, maybe complicated things, but will only do things along this segment in the holographic construction. Whereas in the heavy quark diffusion case, you have the fact that you have a point heavy quark, they have a local modification to the Hamiltonian at each point in time, is reflected by the fact that this extremal surface that is dual to it will be present also at every point in time of the dual description of the Stringer-Kaldich contour in the holographic side. Which from there you can just do the calculation and get the famous result that the diffusion coefficient is pi square root of lambda t cubed in this holographic theory. And well, by doing this, imposing boundary conditions, you get this result, which is qualitatively different because essentially in this second case, you get explicit sensitivity to the thermal density matrix because the string, the modes are coupled through it, so you get these factors of imaginary time evolution. Whereas in the other case, you get something that looks much more like a vacuum correlation function, which leads to the fact that the left-hand side here of the plot goes to 0 instead of just being odd. And well, you can also extend this to finite velocity. You can boost the frame of the QGP by a finite velocity and ask for the correlation function where the heavy quark, where the Wilson line segment is not aligned with the rest frame of the QGP. And what you get is something very natural if you've read the literature about what happens to probes in holography when you boost the medium. You get that essentially that the effective temperature that the heavy quark pair feels is just rescaled by square root of gamma factor, which is the Lorentz boost factor, which essentially reflects that the energy density that the heavy quark pair feels as it flies through it will be enhanced because the medium will be boosted. And well, this is the same as people have found for what the effective temperature that is felt by a heavy quark pair is for the potential between the heavy quarks. So this is a much more microscopic statement about how the two heavy quarks interact. Well, what I described to you just now was just a Wilson line. But here, if you actually separate the Wilson lines and ask, how does the correlation function depend on the velocity when the Wilson lines are separated? You also get you get the same type of correction because of the finite velocity. And well, to finalize, what does this imply for the in medium quarkonium dynamics? If you take the transport formalisms that I showed you earlier and apply this result from holography literally, you'll get something trivial. You'll get that everything vanishes, just simply because the low frequency limit of the correlator vanishes, and because the part that's relevant for the semi-classical description here and has a definite sign of the frequency, which is exactly the part where the distribution functions that I calculated vanish in holography. But then you can wonder whether this actually makes sense if you compare with the QCD result. And so you can plot appropriately normalized spectral functions as a function of frequency over temperature. And you can see that, well, the dashed line here is the holographic result, and the blue, orange, and black lines are the QCD result as you crank up the coupling. And you'll see that, well, even though there are some discrepancies, the general picture is that the weakly coupled QCD result moves in the same direction as the n equals 4 Yang-Mills result lies. So you want to at least have a handle on what the phenomenology is in the case where you're closer to the strongly coupled result. And then, well, as I described earlier, there are more approximations that go into the derivation of these transport equations. And I want to just mention that those approximations can be a bit too strict, because if you simply take and evaluate the density matrix for the heavy quark pair just by doing the most straightforward thing you can do conceptually, which is to take an initial density matrix, time evolve it, trace out the degrees of freedom you're not going to measure, which in this case is everything but the QQ bar pair, and ask for what's the probability of moving from a singlet to an octet or vice versa. You can just expand these time evolution operators up to whatever order you need to get a non-trivial contribution to the transition rate, and you get a non-zero answer, which is just what you get by expanding up to second order this result. And so to give you a figure here, just still preliminary, because we're aiming to do a much more systematic study of this. But the figure here, what it tells you is that if you start with an unbound color state, with an unbound color heavy quark pair, say in the octet, and you let it sit on a plasma whose temperature profile over time evolves in this way, which is a good toy model for what the temperature does in a heavy ion collision. This is what you'd call Bjorken flow. Finishing the evolution at the QCD transition temperature and evolving it for about the 10 Fermi that I showed you in the first slide, a heavy ion collision lasts. And you ask, what is the probability of transitioning from such an octet state to an upsilon 1s state, so the most tightly bound BB bar state, as a function of the initial separation between the two heavy quarks? You get this nice plot where you have where the probability is maximal if the two heavy quarks were separated by the distance that is characteristic to the size of the upsilon 1s state, and then after that you get more medium resonance type contributions to this plot that will also in principle give you something. Of course, the drawback of this is that you can't measure this directly. What you can measure at the end are absolute abundances of how many heavy quarks did I get, and or how many states of how many bound states according to their decay patterns did I get at the detector. So this needs also to be supplemented with a model or with a description of the production of the heavy quark pairs. The background of the quark-gluon plasma also enters here, which here it's just a model. In principle, you could do a hydrodynamic simulation and insert the temperature profile as given by a hydrodynamic simulation. So there's a lot of things you have to do to do actual phenomenology with this, but at least this means that the result at strong coupling using holographic methods, it in principle gives you sensible results. So you should have it as a benchmark to compare the different kinds of observations you can make. Well, and that's it. What I wanted to show you was what theory do you need to build to calculate this very precise physical process, how in principle you can use this to connect to phenomenology. But there's still lots of work to be done. I showed you a calculation in very weak coupling, in a different theory at strong coupling. There's a big question of what happens in between and whether we can actually use this post facto to take observations to learn something about QCD and intermediate coupling using heavy ion collision data, at realistic couplings rather than intermediate couplings. But to do that, we need to improve the transferred formalisms that I showed you before, ideally to have some resummation of the interactions with a medium in a way in which it's not limited by the applicability of time-dependent perturbation theory, which will be very process-dependent, and assess whether the effects that you only see that are dominant in the weakly coupled case are actually dominant in the case where you have a strongly coupled plasma, which is something very interesting to us because it challenges one of the usual assumptions of open quantum systems, where you assume that if you have a weakly coupled system coupled to a large environment, that the dominant interaction that drives the evolution of the subsystem density matrix will be Markovian, so local in time. Here we're getting that the dominant contribution is non-Markovian, so you cannot just write a local in time evolution equation for the subsystem density matrix, which is ultimately tied to the fact that the hierarchy of scales, the mass scale of the temperature of the medium is actually lower than the energy scales of the binding energies between the heavy quarks. So you have to work harder, but it's a fun problem. It has I've spent lots of time thinking about it, and I hope to bring it to a good conclusion in the near future. So thank you so much.
More questions? Bruno?
Yeah, I had a question about your spectral density in the holographic case. There is a high frequency but negative frequency. You're saying it becomes a kind of vacuum.
Yes.
Is there a simple way to see why it's negative frequency and not positive frequency that becomes? Maybe with the spectral representation.
I have thought about this for quite some time. Okay.
Is that at weak coupling? You didn't see this, right?
Yeah, no, at weak coupling, you do see that it's tilting in the same way, but you don't go all the way to zero in one. But at weak coupling, so let me first show you that comparison plot.
It was that one.
It's this one. So at weak coupling, so here I'm normalizing things such that the large positive frequency agree. This is not, so I'm normalizing the spectral function by extra powers of the coupling so that the right-hand side agrees, and I can show you that.
And by agrees, you mean agree with heavy?
Oh, no, among itself. So this is just the rho plus plus that I was showing you earlier.
Yeah.
Here the solid lines are the QCD result at weak coupling that I showed you at first.
Yeah.
and the dashed line is the holographic result that I showed you later. And as you crank up the coupling, well, admittedly, well outside its regime of validity, assuming that, well, and this plotting it in a very convenient way such that the asymptotic behavior towards the right is normalized in the same way. What you see on the asymptotic behavior on the left is that as you crank up the coupling, the result gets more and more asymmetric, and it goes towards the holographic result. Now, why does this happen? If you look at it, if you go to the spectral representation, what is that telling you? It's telling you that, well, it's not that simple, sadly, but it's telling you about essentially what the interplay between what the matrix elements are of these states and what their energies are. And so in a way, if you want to look at omega here, you want to look at plus minus omega at the same absolute value, and you want to ask essentially what's the magnitude of this thing here if I exchange these two. If I change.
But I think so. I think it does make sense that so at a very small time you expect some kind of OP limit where you no longer care about the thermal states in your observable, whereas in the other heavy quark observable you obviously still care because you have this Wilson line going around. So yeah, I think it kind of makes sense that your observable becomes the vacuum answer. I guess that
vacuum-like. It's not. That's not really. I mean, it has more properties has some properties that you'd expect in a vacuum correlation function as opposed to a thermal one. But yes.
So in that sense, it's also more similar to color singlet correlation functions, which will have thermal behavior, but at very large frequency are expected to be vacuum-like as well.
In that sense, yes. That doesn't tell you about the asymmetry between the frequency, positive and negative frequency, but in that sense, yes. And the asymmetry is ultimately due to the fact that, well, as I said here, you have different Hamiltonians, you have different time evolution factors, but
the asymmetry, you could see it in the vacuum.
Yes.
So it's kind of a separate.
The asymmetry. You can
understand it.
start seeing it in the vacuum, but well, QCD eventually you run into problems with perturbation theory if you do it in finite temperature, because well, the famous Linde problem. Actually, the difference in vacuum that I showed you here has so it's purely vacuum if it has purely vacuum consequences if I just have omega cubed, but the term that goes as absolute value of omega cubed actually has some finite temperature effects in a way that I would be more than glad to discuss offline with more formulas. But the reason for this is that this ends up contributing to the value of the transport coefficient gamma that's introduced here to the imaginary part of this through so if you write this out in terms of the Weidmann counterparts and then you use that to write it as in terms of a spectral density. In the usual case, there's a term here that vanishes because the spectral function is odd. But here, when you have even contributions, those give you some thermal effects here that actually contribute to thermal physics for gamma here. Which means that this asymmetry here that I showed you is well, it is something that you can calculate purely in vacuum physics, but it does have thermal implications. And I mean, I showed you that. I showed you the diagrams that contribute to this difference here, and if you can calculate everything here at finite temperature, and you'll show explicitly that the difference for the temperature-dependent part vanishes. But well, if and if you just wrote out the diagrams and added extra legs here, you can get a temperature dependent difference if you go to higher order, just by looking at the diagrams. There's nothing stopping that from happening. The reason why this happens here is, well, it's what perturbation theory gives you.
Any other question? Maybe the same